Hello guys, Jordan here from Artisan Electrics. Welcome back to the channel, and today I am doing the testing on this consumer unit which I have newly installed, and I just wanted to talk you through my testing procedure that I do when changing a consumer unit. Hopefully this video will be of interest to you. If it is, hit a thumbs up, and if you're new here, don't forget to subscribe to the channel and hit the notification bell so that you don't miss out on future videos. So as I say, I installed this consumer unit. It was a replacement for another one which was badly installed and wasn't up to standard. So we've put in this Hager RCPO consumer unit. Now we did carry out an EICR before, so that we knew the state of affairs before we got into changing the consumer unit. So although we have test readings for most of the circuits in the property, we have changed fundamentally the dynamics of the circuits when we've changed the consumer unit. So we do need to do those tests again just to make sure that everything's safe and all the readings are correct. So I'm going to start off, the board's dead at the moment apart from the main tails which are coming in. I'm going to start off by doing an external earth fault loop impedance test, or ZE. This is to basically measure the resistance of the external earth fault loop path to make sure that there's a good earth for the property, etc. So this is what we call a PME supply, or TNCS, which means that the supplier's earth is combined with the neutral at the supplier's neutral block here, which you can see the neutral and the earth come both out of the same terminal. This is the main earth terminal, and what we're going to do is disconnect the main earth conductor from the supplier's PME terminal, and then we're going to use that to test between there and the incoming live at the consumer unit. What I'm going to do as well is I'm going to make a video going through these readings that I have and how I input them into the certificate, because as I go along I'll be inputting these readings into the certificate using my software that I use called Vespula, which is a great online certification software system. So I'll show you how that all works as well. So we'll disconnect the main earth here. Like so. Put the crocodile clip on there. We have the tester on the earth loop impedance high current setting, which is a 2 lead setting, and then we test from there to the live conductor. And we have 0.32, which is acceptable for this kind of installation. It's close to the limit. It should be 0.35 maximum, so it's just under the maximum required, but that's absolutely fine. Now we've got a prospective earth fault current reading of 767 amps as well. We have to take note of that because the next test we're going to do is our prospective fault current test, which will be carried out with the main earth conductor connected. External earth fault loop impedance, or ZE, is always carried out with all the main bonding conductors disconnected. In other words, we're just testing the supplier's earth. But PFC and PEFC, prospective fault current and prospective earth fault current, are always carried out with everything connected. So now I've got ZDB of 0.31 and PEFC of 793 amps, and then now I'm going to do a PFC. So PFC test, which is prospective fault current, in other words the maximum amount of fault current that can travel through the circuit, and that's carried out between phase and neutral. And as it's a TNCS system, you would expect that actually the PEFC and the PFC readings would be similar. So we've got 743 amps there. So the highest, we always record the highest reading that we've taken across all the various combinations. That was 767 amps, so that's what we'll put on the certificate, or 0.76 kA, kiloamps, or 1000 amps. So that's good. We've got our prospective fault current tests done, our external earth fault loop impedance tests, and our ZDB tests done. So now what we have to do is test earth continuity, or continuity of CPCs, we call it, circuit protective conductors. We have to do those tests to make sure that all the final circuits have an earth at the various points. And to do this, what I usually do is use one of these, which is what we call a long wander lead, or an R2 lead, and it's basically a 50-meter long lead which you can then use to connect and test at all the various furthest points. You test the exposed metal work. So basically the crocodile clip here is clipped onto the earth terminal at the consumer unit. The other end of this is connected to my tester. I usually reel out a bit of slack first so that you don't have to keep disconnecting it every time. Quite a big building, so we do that, and then this end goes into the tester in the earth terminal, and the other one, we use this as our test probe to do the tests. We set the tester to the continuity R low setting, and we have to remember to zero out the leads first because we're increasing the resistance quite significantly on the leads. So we zero out the leads. The resistance of the leads is 0.96 ohms. So now when we test, the tester has removed that resistance of the leads from the test reading, so it's giving us an accurate reading of just what the circuit resistance is. And so literally I'm going to just wander around the property now, testing out all the light fittings, the sockets, the switches, etc., to make sure that all the exposed metalwork that needs to be earthed is earthed. So this is an example of a typical test. So that socket outlet, which is quite close to the consumer unit, the resistance of R2, which is the resistance of the circuit protective conductor from the consumer unit to this point, is 0.15 ohms, which is perfectly acceptable. Once the earth continuity readings have been verified throughout the property so that you know that everything is earthed properly, then it's safe to start energizing the circuits using insulation resistance testing. So we don't actually turn the circuits on yet, but first we put energy into the circuits using our insulation resistance tester to make sure that the insulation of the cables is up to scratch and there aren't any short circuits throughout the installation. So we do several tests for insulation resistance. We do live to earth, neutral to earth, and live to neutral. Now, in the case of some installations where there's a lot of connected equipment, you will get false readings doing insulation resistance testing between live and neutral, and there's a possibility of damaging sensitive electronic equipment. So normally we put that as a limitation, or we go around and we disconnect every single light fitting, every single piece of sensitive equipment, but that's in reality that's very difficult to do. So some circuits we will do because we can test without risking damaging anything, like for example the cooker circuit will be fine. The socket circuits, if we unplug everything, then they'll be fine to do live to neutral. But the lighting, for example, and the fire alarm system, we won't do those tests live to neutral, we'll just do live to CPC and neutral to CPC. So we'll start with circuit number 1 and we'll just work our way across. Now the tester has several voltage settings for insulation resistance. You have, it goes up from 50 volts to 100 volts, 250 volts, 500 volts and 1000 volts. Now it's recommended to test an installation that will normally run at 230 volts, that you should test it at 500 volts. However, if there's a risk of damaging sensitive equipment, then we can rather just test at 250 volts to make sure that there's no risk there. I will test at 500 volts between phase to earth and neutral to earth and see what we get. So we'll start with circuit 1, which is the air conditioning units. My tester's got stuck for some reason, so I might need to try that again. Okay, probably because I'm testing at 500 volts, there's some kind of interference. So I'm going to just test at 250 volts and turn my pre-test setting off and see if that does the trick. Yeah. So we've got 70, 80 mega ohms and rising, neutral to earth. We have the same. Next circuit, circuit 2, same kind of readings. Again, it's got stuck for some reason, I'm not quite sure. Oh, there we go, it's clear, 200 mega ohms. That's good. Now the cooker circuit, and that's clear, we've got 200 mega ohms there. One thing I meant to say is that in order to make sure you're testing all of the cabling throughout the property, you need to turn on all the switches. So turn on all the light switches, for example, to make sure you're testing not just the cable to the light switch, but from the light switch to the lights. And same with things like the cooker switch. So I'm just going to go and turn the cooker switch on now, because I forgot to do that. Right, so let's try that cooker again. And that's still fine. 200, greater than 200 mega ohms. If I do live to neutral on the cooker circuit as well, should be fine because nothing's turned on yet. So then we go to our sockets in the kitchen. Again, unplugged everything so that's all nice and clear. Okay, live to neutral I've got a short, but that's because there's a fan isolator which is turned on at the moment. So that's reading through the internal circuitry of the fan. So that's what I meant about, you know, being in danger. If I put 500 volts live to neutral with that fan connected, it would blow the fan up. So this circuit we've got phase to CPC 200 mega ohms, but neutral to CPC is a little bit lower, 22.6 mega ohms. Still acceptable because the readings should be over 1 mega ohm. So that's still fine, but something to think about. If a circuit is close to the borderline, then I would usually do some investigation, but if it's up in the 26s, like this one's in 26 as well, it's probably due to just some connected equipment. 21. So sometimes it feeds back through the main PME block as well, and so you'll get readings that are a bit funny because of that on the neutrals. Yeah, so all the neutrals are going to be the same, I think. Lighting, 21, 22, but again that's because the light circuits are turned on. Now what you can actually do, in fact maybe we can just do this for fun, you can test through all the circuits if you want to. So if you just test from the bus bar, see I've got 20 mega ohms, so I know that actually everything's fine, and I can do the same with this, neutral to CPC, 29 mega ohms, so I know that actually everything's fine. If it wasn't, if say for example one circuit was shorting out, how how would I do that? No, I can't actually do it that way. But if any one circuit had a low reading, it would bring the readings of the whole lot down. So that's actually quite a quick way to do it. On a new installation, it's possible to just do it that way. If there are, if it's in the ICR and there are lots of dodgy insulation readings, then it's difficult to do. And in fact, usually what I do is disconnect the neutrals and test one by one each cable, just to get accurate readings. But in this case, I'm happy with that, 29.2 megohms. I'll just test anyway because I'm nearly at the end, so I'll just test the last few individually just because I can. All good. Actually, I left the circuit breakers on, so that was testing across all of them anyway. Right, so that is insulation resistance done, continuity of CPCs done. So the next test that we do is continuity of ring final circuits. And in this case, we've only got one ring final circuit, which is this one, 32 amp. We've got 2 cables in there. So we've just got to disconnect these and disconnect the earths and then do a continuity test to make sure we do have ring continuity. So for this I usually use 2 crocodile clips. And a pair of long nose pliers comes in quite handy usually on this test, just to neatly lever the things out. So that's circuit 4, so I go 1, 2, 3, 4 and it's this one for the CPCs. Nice pair of Nipex long nose pliers, and we just can gently lever those 2 out. Like that. Same with the phase conductors, and same with the neutral conductors. And this way it's easy to put them back in neatly because I've made so much effort making sure that the bend radiuses were all the same on these that if I just lash it out, it's going to ruin all my hard work. So I've got to zero my leads again because I zeroed them to my long wander lead. Now I've only got these short leads, so I've got to zero them. There we go. And we'll start by doing the continuity of the phase conductor, as that's the order that it is on the certificate. 0.27 ohms. Then we'll do the neutral conductors, 0.29 ohms. And then the CPC conductors, 0.49 ohms. So that's good, very good readings. Now there's another test that we need to do as well with the ring final circuit, which is to check that there aren't any interconnections. And for that one, what we do, it's usually on new builds, we connect one leg of the live to one leg of the CPC, and the same with the other, and then we test R1 and R2 at the socket outlet. I'm not going to do that in this case because I don't think it's really necessary, and it's going to ruin my bend radiuses on my cables if I do that. But just so you know, there is another sort of ring test that it's not on the certificate, but it's down there as an option, and a lot of people recommend that you do it. So now I can neatly put my cables back in. Good. So now we've actually completed all the operations that would require us to unscrew anything within the board. The next set of tests is live testing, where we test the earth fault loop impedance at the end point of each circuit. So for that we can actually put the board cover back on Oh, but we need to do RCD testing first, and what I usually do for ease of process, I do the RCD testing here at the board rather than doing it at the end of line and having to run back and forth. So what I'll do first is do the RCD tests on all the circuits, and then once that's done we'll do a fault loop impedance. So for the RCD tests, this fluke tester has an auto test function, which is quite good. Now these are type AC RCDs. No, sorry, type A RCDs. So they test both AC and DC fault current. So I'm going to have to do 2 sets of tests on each of these RCDs. So I'll select it to auto setting, turn the main switch on, and then turn the first circuit breaker on. The first test that we do is just a push button test, so press that and it should trip. That's good. Then we do the RCD test, and it measures half times at 0 degrees of the sine wave, then half times at 180 degrees of the sine wave, and it shouldn't trip. Then at 1 times it should trip, and it does 2 tests, 0 degrees and 180 degrees of the sine wave, and then we do 5 times the current rating, which is 150 milliamps, and that should trip again, and we do 0 degrees and 180 degrees of the sine wave once again. So that is our first set of tests done. Then we need to switch the tester to the DC setting for the pulsating DC, and then we do the same. So we run through another 6 tests, and again at half times it shouldn't trip. At 1 times it should trip, and it does. And there we go. So we've got the highest readings there. 5 times was 12.7 and 1 times was 12.3. So that's fine. And then we just do the same for all of these circuits. So just run through that for the whole lot. It's a little bit tedious, but it gets it done, and we write down the highest readings each time. Right, so I've got all my readings here, and you'll notice that actually circuit 4, the testing there gave me error 4 on my tester, and then the 5 times testing was more than 50 milliseconds. So I've left that circuit off, and I'm going to swap out the RCBO. Hopefully it's just a faulty RCBO, and then hopefully that should do the trick. Fortunately, because I do a lot of Hager installations, I do carry some spares, and I've got a spare 32 amp breaker there. So I've just turned off the main switch, but I'm just going to check to make sure that everything is dead before I start taking the bus bar out or disconnecting the breaker. So just going to test on the outgoing side of the switch, and that is fine, that's all dead. And then I'll just prove that it's dead by checking my tester again. All good. So, the great thing about Hager is that you can literally just take one circuit breaker out without having to take the whole lot, the whole bus bar out, because they've got these little clips, these little bus bar clips underneath, which go, they go all the way down. Hard to sort of describe, but if you've dealt with them before, you'll know what I mean. So it can literally lift right up high enough to come off the bus bar. Just need to lift those out a bit more. There we go. And I'll need to disconnect this, so it's the fourth one along. 1, 2, 3, 4. Disconnect the neutral tail. Typical, isn't it? That it has to have one dodgy one that messes up my whole nice, neat array. But anyway, there we go. So that will pull out. And then, I bet you I'll change this and it'll still be doing the same, and it will be some kind of problem on the actual circuit rather than the RCBO, but there's no way to really know. That's the trouble. I mean, the insulation readings are okay on this circuit, so all I can think is that it's faulty RCBO, but right, lever that. So I'll show you what I mean now about these clips. That lever's really far down and it stays down, and that means that essentially you can access the bus bar like that, and a bit more, that's it, like that, and it slots down. Then you click the clip up and then you tighten it back onto the bus bar. There we go. Get my outgoing cables back in. Tail back in and try and do it neatly. This is where these long nose pliers come in really handy. And you can just use them to hold the wires in place while you tighten them, because sometimes it's hard to hold them with your fingers. You just can't get your fingers in to the right place. That's it. So we managed to do that without messing things up too much. So we'll turn the main switch back on now, and then I will do some tests on this one and see if it's still the same or if we've got good readings now. So first turn it on, press the test button, that's all good. So we'll do an auto test on the AC side first. Error 4 still. Error 4 again. 37.9 5 times. Greater than 50 milliseconds. How annoying. So there must be something funny going on there. Let me just do insulation resistance on here again, just to see what we've got. What? I've got 0 now. That makes no sense. I've got 0 mega ohms lifetime. Life to earth and 0 megohms life to neutral. How is that possible? Completely 0 and 60 ohms. It's not possible. It would go bang if that was the case. Oh man, I don't get this. Right, let me take this out. Main switch off. So let's try it without anything connected. See what's going on. Right, we've got 180 megohms there. Got 200 megohms there. If I test this, now that's all clear. 24 megohms, but that's just going through the neutral because it's not a double pole RCBO. And if I turn the main switch on, zero. Tester seems to be working okay, but this is giving funny readings. I don't know why. So I'm going to check what's on the circuit. Maybe there's something connected that shouldn't be. It is the sockets in the kitchen. Right, there was a fridge that was still connected. So I'm hoping that if I reconnect this now, it will actually be okay. Fridges are funny things. They have funny equipment in that can give dodgy readings sometimes. I've had it before. It's really annoying. I think it's the compressor inside, or whatever you call it. The heat exchanger type thing, that all the wizardry that goes on inside a fridge anyway, it seems to cause havoc to RCDs. So, try again. So let's do RCD auto. Looking better. 17.2, 6.8, 16.7. Brilliant. Let's try the DC side. I should have thought of that first, rather than changing the flipping breaker. Anyway, 7.2. 16.9, 16.8, 17.2. There we go, fine. So I can add that as my last reading. 16.9 and 17.2. Great. So that's all our RCDs are fine now. I need to just swap the sticker over onto that one from the other one that I removed. There we go. Good as new. So now that all the connections are kind of done, we're not going to be removing anything or putting anything back, I'm going to torque up all these screws now. That's really important to make sure that they're all tightened to the correct torque setting. As I mentioned when I did the consumer unit installation video, when I first do the installation I just tighten them up hand tight, shall we say, not tight as they should be, but tight enough to provide a secure connection. And then at the end, once I've finished testing everything, I go through it and do the final torque tests. It's not going to make any difference to the readings, but it's more about the mechanical soundness of the terminations. So I've got this Vera torque screwdriver, and on the cover of the consumer unit here it has the torque settings recorded for us. So all we need to do is copy the readings from here onto the screwdriver and then tighten up the correct terminals to the correct tightness. So it starts with the earth and neutral bars, PZ2, cables greater than 1.5mm should be tightened to 2nm, and cables less than 1.5mm to 1.5nm. So I'll start with 1.5nm on here. Nm stands for Newton meters, by the way, that's a torque measurement. Go all the way down to 1.5, which seems quite low. There we go. So, any conductors less than 1.5mm, which are basically the lighting ones. So I'm getting a little bit of a turn on those, not a huge amount, but just enough. Okay, and the neutral ferrules are also 1.5mm. So I'll tighten those up to 1.5nm as well. Okay, so any conductors greater than 1.5 we should do to 2 Newton meters. So I'm going to set this to 2 Newton meters now. There we go, and basically these ones, so the large neutral tails for the 32 amp circuit breakers. And then all the earths, the larger earths. Fine. Then, isolation switch disconnectors 3.6 Newton meters. So unfortunately this torque screwdriver only goes up to 3 Newton meters. So I'll do that at the end. MCBs and RCBOs, we need 2.1 Newton meters on all of the connections. So we'll go up by 1 Newton meter and we'll just do all of these. You can see how much more torque we're getting on these. And that click, by the way, is just so that it tells you when it's reached the correct torque. Okay, and the Looks like the bottom connections on the bus bar should be the same. Main switch should be 3.1, so I'll just go up to as high as I can, which is 3. And then what I'll do for the main switch is just give it a tiny bit more, if I can. There we go. So that should be fine. Good. So now our final set of tests are our earth loop impedance tests, which are done at the furthest point on each circuit. And we take a resistance reading there to make sure that the earth loop impedance at that point is not too high that the circuit breaker will not trip in the event of a fault. So we will start at the front and work our way through all the circuits until the end. So I'm going to start at the AC units outside. So we're going to take the cover off. Turn the isolator off first, so the outgoing side is dead at least. Obviously earth loop impedance tests have to be done live, so you have to just be very careful and make sure that you're using the correct test leads that are acceptable for testing on live. So I've got my crocodile clip, which I'm going to put on the earth conductor, and then I can just clip that onto the earthing terminal there, and then the phase and neutral conductors I will use my dab on leads, setting it to the non-trip setting as it's got RCD protection on the circuit, and then going onto the incoming side of the isolator, and we have power. So I press the test button, hold the leads on nice and firm, and we've got a reading of 0.43 ohms, which is excellent. There are a table of maximum readings that you have to abide by. So this is a 32 amp type B circuit breaker for this one, so it's 1.15 ohms I believe for this size of breaker. So 0.43 is way below the maximum, which is great. And we can do the same for this one. It's a lovely sunny day. So we've got 0.7 on that one, which is a bit higher than the other one. I'm just going to test that again just to make sure that my leads were it's even higher now, 1.11, which is a bit weird. So 0.42. So I mustn't have had a good connection on the crocodile clip. That's what it should be, because both of these circuits are the same length, so the readings should be identical really. If they're not, then you question whether there's a weak joint somewhere, a loose connection or something like that. Because the resistance of the cabling is the same, the cable sizes are the same, so the readings should be the same if they're the same length. So I do the same here for the cooker. I'll just turn the isolator off while I take the cover off for this. It's just one of those ones that pops off anyway, I think, so it's easily done. There we go. Turn that on. Again, we'll use the crocodile clips on the earth. If they'll stay on. And then live and neutral. .54. That'll do. So next we're going to be testing the socket outlets here in the kitchen, and they're really easy to test because all we do is plug it in and then do our test reading. I usually like to test all of the sockets just to make sure that the polarity is correct on all of them. So we've got 0.75 there. .73. There's one under here, so I'll test that, and then over there is a switch fuse connection unit which is for the fan, so I'll test that one as well. So I hope that video was a benefit to you and you enjoyed watching it. If you did, don't forget to hit a thumbs up, and if you're new to the channel, thanks for watching. I hope you'll subscribe and hit the notification bell so that you don't miss out on future videos. And let me know in the comments what you thought about the testing procedure. Have you got any tips for me? And let me know if you do things slightly differently. I always read your comments and I try to respond as much as I possibly can. Also, let me know in the comments if you would like me to post a second follow-up video to this with all the certification side of things and filling out the forms. I'd love to know, and I'll prep that video for you soon if there's enough demand. Thanks for watching and have a great day.